electron forms the bond between the atoms, and atoms form the molecules of all living organisms. Our microscopic world is rarely static. In most cases, our microscopic world is in motions, no matter how high its spatial resolutions. A traditional microscope. Such a microscope can capture the dynamic happening all the time in microscopic world. To be able to freeze the motions of the fastest particle in our world, we need to be able to do microscopy in time. And that's exactly what can be done with a short laser pulses. If our camera's exposure time is too long, the fastest object will appear in our photos and eyes will blur in the normal cameras. We have a machine that turns on and off, and we can do it electronically, but we can't do it faster than a microsecond, about a millionth of the second. These are the fastest camera which can actually even capture the motion of a bullet fired from the gun. However, this technique can't be developed much faster. We have to come up with some new idea. These new ideas are flashes of light, basically making a very short flashes and illuminate object you would like to capture the motions of which one would like to capture with very short flashes, and this is only possible with the laser. The trick to generate them is that actually we make a laser emit continuous wave at many different frequencies in such a way that at certain instant in time, maximum of one of the oscillations of each of these wave of a different frequencies coincide, and that's the moment when the correspondingly sum of all the waves builds up to very high intensity, and this is the peak of the part. To generate even a shorter flashes, to be able to capture eventually a motions of electron, and the idea was really intrinsically simple. Just make sure that such a single cycle laser pulse, it has a strong enough electric field that is able to rip off one electron from the atom, and this procedure of ripping off electron requires the electric field to overcome the certain thresholds. So if you now imagine this electric field in our short pulse has basically a single half cycle in the center, and then only a small fractions of the single half cycle delivers a strong electric field, or you can say strong enough electric field for this process to activate, and therefore this ripping of electron can happen within the fractions of this half cycle of our laser pulse, and these fractions actually means a fractions of the femtosecond. So we indeed manage to generate in this way extreme ultraviolet flashes of light. Back in 2001 turns out to be 650 attoseconds. From here, the field of attosecond physics was born. Attosecond physics is a research area that's just a little more than 20 years old, and so it mainly employs a pump probe spectroscopic method to investigate the physical process of interest. Due to the complexity of the field of the study, it generally requires a synergetic interplays between the state of art and experiment setup and the advanced theoretical tools to interpret the data collected from the attosecond experiment. Obviously, we can't see the electron itself because it's that incredibly teeny. We can just measure the properties of the transmitted flashes of the light, and the electron with which this very short attosecond flash interact leaves its imprint on transmitted flash of light. So if we analyze this transmitted flash of light at a second light, we can learn about the instantaneous state of electron at a very moment of the flash. The ability to modify the electron behavior could lead to ultra-fast switches.
The research could potentially convert an electric insulator to conductor on attosecond scale to increase the speed of electronics. Electronics currently process information at picosecond scale or 10⁻⁻12 of a second. A short wavelength of attosecond pulse, which is typically in extreme ultraviolet or EUV regime, may see the applications in EUV lithography. In the semiconductor industry, UV lithography uses a laser light with very short wavelength to etch tiny circuit on electronics chip.